Okay, back to answer the door. Standard error of the x bars. I'm going to call this one 3a, just a continuation. Standard error of the x bar equal to the estimated standard deviation of the population. We're using the sample there, divided by the square root of n. Really weird things are happening here. So this is equal to, in our data, the standard deviation is 17. So it's 17 divided by the square root of 10, which is going to be about 3.16, equal to be about, it's going to be about 5.38. And we're going to build an interval using that standard error. We're going to first double it, because remember, we want a 95% interval. So we're going to first double it, so we got what, about 10.8? Let's call it 11, just for fun. So let's say twice the standard error, about equal 11, and we know that two standard errors one way plus two standard errors the other collectively is going to cover 95% of the area. So let's figure out. Let's go 11 back from here. You can do 77 minus 11, 66. Let's put that out right here. And then add 11 on the other side, right? So it is 88. All of these, of course, approximate. And the normal curve around these is going to look something like this. And 95% error is in here. Not too bad, artistically, for a very challenged person. Like myself, I've built a 95% confidence interval around what I observed with 10 observations, 77 equal x bar, under the assumption that every pull from the population to make these x bars was made at random and with replacement. So you find an x bar, throw your 10 back, sample at random, on and on and on and on. Now I have confidence interval around my sample mean. It's huge. It's more or less useless. It's huge and more or less useless because, if it's true that what I want to do is estimate the population mean. I want to estimate the grade, the average grade made across all 13,000 of the students, and look at all the numbers that are included in here. Inside the 95% confidence interval lies the grade 87. So inside the 95% confidence interval lies the grade 67. And remember, these are approximate. It'd really be 1.96 if we had enough data. This is a terrible result, and it's not even statistically correct, because another tenet of the central limit theorem is that the sample size needs to be sufficiently large for it to kick in. When we do this in class using R, you're going to see, actually visualize, what happens as the central limit theorem kicks in. It will kick in a serious way until about 20, and then 18, 19. You can see it, but everything's unreliable. But we can manipulate our problem here because we made it up. So instead of 10 for a sample size, let's think of 100. That's really easy. A sample size, let's suppose we drew a sample of 100 and then drew a billion other samples of 100 and found a billion other x bars, this time each with n equal to 100 instead of 10. Then you've got this problem here becomes 17 divided by the square root of 100, which is 10, right? And in your head you can do that as 1.7. And then you're going to double that. So we're going to erase these old ones and redo them. So you're going to double 1.7. So you've got still here working from 77. Going to double 1.7, right? 3.4. That's how far we're going this time. Let's go about 3 and say, so we're rounding here. Let's go to 74. And let's go over here about 3, which would be about 80. And now your normal curve is much skinnier. It's much skinnier. It would have been, I should have made it bigger and taller because it would include the same number of X bars in theory, which is all of them. But now see, we're 95% confident that if we drew another sample of 100, that it would produce an X bar that would fall into the interval between 74 and 80. Now we're getting somewhere. Now we're getting somewhere. And what happens if you move upward to 10,000, if you move to 10 sample size of 10,000, then you've got the square root of that is 100. So you continue to assume that it all then becomes much, 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 much smaller. So as the sample size races upward, according to the square root of n, the boundaries on the confidence interval move inward and you become increasingly confident that if you drew another sample of that same size, that it would produce a result that's actually quite close. Interestingly, you never get there. So we had here hypothetically a population value of 13,000. Well, if we did 13,000 X bars or 100 million X bars, we would never shrink our estimate of what's known as, and now this is it, the sampling error around the mean. We would never shrink it all the way to 0. You never get there, and you become to get more, you sort of move there less quickly than you do in the first few bumps from, it was a really huge bump you see there from 10 to 100. Big bump from 100 to 1,000, the bumps become smaller there and they never finish. So now you have done a confidence interval and you are the enemy of everybody who's Bayesian. So next thing we're going to do is an example that formalizes this a little better or in a little more discrete way. And then we're going to look at the sample proportion, which is its own special beast.